This is the code explanation for the beat generator that was implemented on a Z-board FPGA. The top module is the top VIO module, and it instantiates the VIO ILA and the actual top module of the program. The VIO and ILA are used to verify the functionality of the code. The top one module instantiates the working modules of the program. Um, that includes the switch handler, the beat generator module, and the LED driver module. The way the beat generator is implemented is using counters. So this is the counter module. Whenever the passage of the clock is detected, it checks if reset is set. If reset is set, the counter value is set to 0. Otherwise, the counter value is incremented by 1. So this is an up counter at every positive clock. This counter is used in the beat generator module. As we can see, at the positive edge of every clock in the beat generator, it first sees what the switch value is in this big if statement. If the switch value and the counter value match, it resets the counter. As we can see for all the different values. The -2 over here is because we want the counter reset signal to be high one cycle before we want the actual counter to be reset. We also want the count reset to be high only for one cycle, so that's why since we want the count reset to be high only for one cycle, the moment it is set high, it is immediately set low the next cycle. And for all the other operations, the count reset is set to 0. Also, we generate the pulse whenever the output of the counter is 0. So this means that the pulse will be high only for one cycle. So let's say the count ends at 60. Um, the counter will go up to 58, 59, and then go to 0, and then go to 1. So this way, pulse is active only for one clock cycle. So the beat generator instantiates the counter, and it uses the count reset logic and the reset that appears from the input of the beat generator. The beat generator receives a reset from a switch handler. This switch handler detects if the switch has changed while the counter is counting up. So whenever the switches have changed, um, the counter is reset back to 0 so that there are no issues with timing. As we can see, the switch handler module stores the previous state of the switches. If it matches, then force reset is set to 0. If they don't match, force reset is set to 1. Finally, we have the LED driver, which drives the output. The LED driver detects positive edges of the pulse. And if the positive edge of the pulse is detected, it switches or toggles the output of the LED, as we can see in this line. Otherwise, if reset is high, it sets the LED to a 0 initial state. Also, the input of the LED driver, the input clock, is given by the pulse signal over here. All of this is combined together in the top module, where the output pulse of the beat generator is sent to the input pulse of the LED driver. And the output of the LED driver it's sent to an LED.
This is the BPM. This is the pulses, the LED. Okay, and this is currently in 00 state, which corresponds to 60 BPM. Yeah. So this is in state 001. As you can see, the blinking rate change. This is to 010. These are our control switches. This three, and this is in 011. This is in our 100. This is 101. This is 110. This is 111. Let's set it in any random random state and let's just check what the pulse is. So this is to control the reset, and as you can see the other LED blinks. We said we send a reset signal, and yes, that's it. This is the ILA implementation, the IO implementation. So currently reset is 0 and our initial state is H. So let's set it and let's test it. Okay, so it's currently completely 0 and we can't see any blinking here. Okay, so let's change the value, reset to 0, and we can see since it is in 000 state, the blinking goes on. And now let's move on to next value. Let's move on to h equal to 1. This corresponds to 001 states, which is 90 bpm. Yes, as we can see, the value changed. It beats. One second. Diagram. No. Yeah. Here. One second. Yeah, I run this. Now let's. We can see. Can you zoom it? Zoom it more. We can see at 66666, since it goes from 0, so at that counter time it generated a pulse, this one. Okay, so now we will move to different value. Let's change our trigger. Here is the pulse. Okay, let's change it to 2. We can see the beat rate change and we will see it in the diagram. Can you run it? Yeah, and see, it goes till 50 into 10 raised to the power 6 zeros, since it starts from 0. And let's change it again to 3. This is the fourth state. Run it. It should go to 40. Perfect. This works, and you can see the beat speed changed. Yeah. Let's go to 4. Okay, it's at 30. Beat speed changed. Let's again move. Yeah. Tap. It will go to 20. Perfect. As we can see, the beat speed is different. Yeah. H equal to 6. And we can see again it changed to, it was for the 1200, and the pulse rate changed. For the 7, let's see, this will be our fastest. And see, basically this is a counter which, when completes the count based on the parameters given in the code, it sets on a pulse when the count completed. Just a counter that is used to create a pulse generator. These are the counter values, as I can show. This is for every 60 bpm, and correspondingly these are the values based on the file given us in the project.